In lesson 6.1, we were introduced to antiderivatives and this process of integration. And that's a tool that's going to help us to solve the area problem. We mentioned in the beginning of the class that calculus is really used to help us solve two problems in mathematics. One of them is to find the slope of curvy functions, and the other one is to find the area of regions that have curvy boundaries. So that's what we're going to take a look at today. We're going to talk about area, and actually in the second part, the second video of this lecture, we'll get to the definite integral. So if you studied geometry, you have some experience with area, particularly common shapes like rectangles, circles, triangles. We have specific formulas to find the area of those regions. Here we happen to have a graph of a constant function, y equals 1.2, and the area underneath that curve here is easy to find. It's simply the length, the base, the length here, which is 4, times the height here, which is 1.2, and a little multiplication, and you'll figure out that the area of this region is 4.8 square units. In particular, in this case, this graph is about petroleum consumption, and the total consumption in this area, represented by this area, is 4.8 million barrels. Now, the area problem becomes a little more complicated when our regions have curvy boundaries. Here is another function that represents petroleum consumption, but this time the upper boundary is not a horizontal line. It's a function of x that happens to be curvy. So finding the area represented by this region here is simply not as easy. So we need a plan. We need a plan to find the area under the graph of a curve, f, on a closed interval, in this case from A to B. We need a plan for figuring out the area that's enclosed underneath that curve. And there is a plan, which I'm going to outline for you in the rest of this video. So first we're going to start off by defining area. And basically we're going to focus on regions that we know how to find the area, and use those to help us find the area of these curvy regions. So here's the strategy. Let's take a look at a function, a familiar function, x squared. And you can see the graph of x squared is down here. It's this blue curve. And then if we focus on the interval from 0 to 1 on the x-axis, we can talk about region R here, which is the shaded area underneath the curve f of x equals x squared. So our plan for figuring out the region, the area of region R, goes something like this. We're going to start by adding several rectangles to our picture, and we're going to approximate the area. Now the choice of the rectangles is specific, so that the math involved can be related to the other concepts we've studied. What we're going to be doing is breaking up this interval on the x-axis into subintervals. Our subintervals are all going to have the same width. And from those subintervals, we're going to make rectangles. There's a couple of different ways we can do this. We can make a rectangle by looking at a particular subinterval, like this one here. And then we could use this height to make a rectangle. Or we could look at this subinterval here. We could use the right-hand side to make a rectangle. Or if we're looking at this rectangle here, we could use the middle to make a rectangle. The point is that we know how to do the area of rectangles, so if we can make this region into a bunch of rectangles, we can add those up and get an estimate for the area. Here's one way to break up that area underneath underneath x squared, that region R, into 4 rectangles. In this case, the subintervals are all 1/4 in width. And what we've done is we've taken the midpoint of each of those subintervals and used that function value to figure out the height of our rectangle. We use the midpoint of each subinterval to find out the height of our rectangle. And then we go ahead and draw that rectangle. Now don't get me wrong, there are issues with this strategy. We are missing gaps here. And we're also adding on extra stuff here. So this is just an approximation. But it's one way to get a handle on this concept of a region that's bounded by a curvy boundary. One way to solve the problem of the extra pieces and the gaps, or the missing areas in our picture, is to increase the number of rectangles. Notice with 8 rectangles, we get much closer to finding the actual area of region R. And if we use 16 rectangles, now we're on to something here. So the more rectangles that we use for our approximation, the more accurate it looks like it's going to be. So here's a table that shows the areas for a certain number of rectangles. For 4 rectangles, the approximation is 0.328125. You can see that decimal. And notice, as we increase the number of rectangles, it appears that we're heading toward a limiting value. My best guess says that we're heading towards 0.3 repeating, or 1/3. We increase the number of rectangles, we get a much more accurate approximation of what we think the area of region R is. So what I'm trying to do here is break down for you the calculations that we're going to need to make in order to find an approximation for the area of a region. The first thing I want to do is identify the number of subintervals that we need, the number of rectangles, right? This n is really the number of rectangles that we're going to draw. And in our problems, that'll be given to us. We'll say approximate the area with 4 rectangles. And that tells us that n is 4. Once you know what n is, you can figure out your subinterval width, because each of our rectangles is going to be the exact same width. The way you do that is you do b minus a over n. And the b and the a come from the interval. So in the problems, you're going to be given an interval, a closed interval. A is the left-hand point on the x-axis and b is the right-hand point on the x-axis. You figure out how long your rectangles are by doing b minus a over n. Typically we'll call that delta x, but it's really just the width of the subintervals. The next thing you're going to want to do is, you're going to want to find a partition of, not a partition, you're going to want to find a list of representative points. We call those x sub n. And the way you do that is you identify which end point of the interval you're going to use, or if you're going to use a midpoint. And then that's the x coordinate that you'll use for that rectangle to figure out the height. You'll plug x sub n into the function to figure out the height of that rectangle. We will either use the left endpoint the right endpoint. I guess that's supposed to say left. This is the comic relief portion of the video. I'm just going to speak it instead of write it. The left endpoint, the right endpoint, or the midpoint of the interval. And then finally, the area of any given rectangle is going to be the function value, which will give us the height of the rectangle, multiplied by the width of the rectangle, which we call delta x. Now again, these representative points are going to be specific. We'll say use the left-hand endpoint of each subinterval, or the right-hand endpoint, or the midpoint. And the best thing to do is make a list of those ahead of time. x1, x2, and so on, so that you know which values to plug into the function. And that'll happen here. That way you have a list of heights. Finally, once you have a bunch of rectangles and you know their areas, you simply add those up, and that's an approximation for the area of your region. Remember, it's an approximation because those rectangles don't match up smoothly with the curve. So I've been talking a lot and I haven't done a lot of math yet, so I thought it'd be a good time now to show you an actual example where we are going to find the approximation of a particular region. In this case, we're going to focus on the function f of x equals 16x squared. 16 minus x squared. And the particular interval that I'm interested in is between 1 and 3 on the x-axis. So my a is 1 and my b is 3. And you can see here that we've indicated the region R to be that region between the curve and the x-axis. The right and left boundaries are x equals a and x equals b. The task that we're asked to carry out is to find an approximation of the area with 4 subintervals, meaning we're going to have 4 rectangles. As you know, we're on the interval 1, 3, and our intervals are of equal length, which we mentioned before, and we're going to use the left endpoint. Ooh, that's interesting. I didn't make that green there. Again, that's another one for the blooper reel. We're going to use the left endpoint of each subinterval to evaluate f of x. In other words, that's how we're going to find the height of our rectangle. Okay, so let's attack this problem. First thing, as you know, our interval is 1, 3. Our function is f of x equals 16 minus x squared. We are going to use 4 rectangles, so our n equals 4. And from that we can figure out that our delta x is 3 minus 1 over 4, which is 1/2. Okay, so that's our setup. Now let's get a picture of this thing. And the picture looks something like this. As you know, on the last screen we had a nice pretty graphic. For this particular sketch, you're going to be stuck with my interpretation of that picture. And I'm looking at the interval between 1 and 3. So there's a 2 in there, right? And then this is 4. And 16's way up here. Okay. So we're focusing on the subinterval between 1 and 3. We have our delta x, we have our n, which is our number of rectangles. Now what we need is our representative values for x. If we're going to draw 4 rectangles, and we're going to start at the point x equals 1, this is our starting point, then our list of subintervals will be from 1 to 1.5, from 1.5 to 2, from 2 to 2.5, and from 2.5 to 3. Those will be the points that we will make our rectangles with. 1, 1.5, 2, 2.5, and 3. Since we are using the left-hand endpoints, our x sub n's are just going to be these 4 values here. 1, 1.5, 2, and 2.5. We won't use the 3 because that's a right-hand endpoint to our rectangle. See, our rectangles are going to look like this. We're going to use the left-hand side, so we draw that rectangle. We draw that rectangle. This is going to be an upper estimate because every single one of our rectangles is going to be outside of our box. So we have 4 rectangles, and we're going to use the right-hand value to figure out the height of each of those rectangles. Oops, this one really should point here. Okay. So we're going to do f of x1 times delta x, f of x2 times delta x, f of x3 times delta x, f of x4 times delta x. As it turns out, you can factor out that delta x, that 1/2, and just add up the f values. So our area is going to be approximated by the following. F of 1, which is 16 minus 1, because 1 squared is 1, so that's 15, plus f of 1.5, which is 16 minus 1.5 squared. 1.5 squared is 2.25, so 16 minus 2.25 is probably 13.75. F of 2 is 16 minus 2 squared, which is 16 minus 4, which is 12. And f of 2.5 will be 16 minus 2.5 squared. 2.5 squared is 6.25. 16 minus 6.25 is 9.75. And all of that is going to be multiplied by 1/2. I'm going to squeeze it in right there. Okay, I've done a little calculations, and if I'm correct, this entire value here is 50.25. Excuse me, 50.5. And I'm going to multiply by that 1/2 or divide by 2, however you want to look at it. And so our approximation for 4 rectangles is going to be 25.25 square units. I'll quickly remind you what we did. We identified our interval, our function, our number of rectangles, and the width of each rectangle. Delta x is the width of each rectangle. Based on the fact that we're using left-hand endpoints, we looked at our subintervals and we took the left-hand endpoint of each subinterval, which is just these 4 values. We plug those 4 values into the function and we get these 4 heights. Add those together and then divide by 2 because our delta x is 2, and we end up with an area approximately equal to 25.25. Now, as we mentioned previously, as we increase the number of rectangles, we're going to get a more accurate estimate for the area under this curve. You can see here with n equals 4 rectangles, we came up with a 25.25 approximation. If we were to increase it to 10 rectangles, we'd end up with 24.12 and so on. And as you can see, this value starts leveling off at what looks like is going to be about 23 1/3. So for this video, I just want to stop and end with a summary of what it is that we're writing down when we do these approximations. This is all discussion of area so far. We haven't talked about definite integrals yet. We start by identifying our function and the interval that we're going to use. We sketch the graph. We find out how many rectangles we're going to have. We figure out the width of each rectangle using delta x. We make a list of those subintervals, and then we make a list of those representative values. These are the values that we're going to plug into the function. We plug each one in, we multiply by delta x, and then we add those up. Finally, make sure you're always answering the question that's posed. So this is an introduction to area. I'm going to do a separate video where I go through another couple of examples from the text, and then I'm also going to post about definite integrals. Good luck.